As we've seen in earlier work in this topic, a lot of salts are not actually neutral, even though they're often made by neutralization reactions. So ammonium chloride is a very good example of this, and we can see that here that we're given a pKa for the ammonium ion. That's a bit of a giveaway that there's more happening in this salt than just dissociation when you put the salt in water. So what we actually see happening here is if I had ammonium chloride that's solid and I put it in water, then it turns into ammonium ions that are aqueous and chloride ions that are aqueous. Chloride ions don't go on to react with water, so they can basically be ignored. Their concentration will be 0.02 moles per litre because it's a 1-to-1 ratio with what's at the start, and so will the ammonium. However, aqueous ammonium will dissociate a bit when it's put with water, so I need to write a second equation. And in this case, the ammonium is going to donate one of its protons to water to make hydronium ions in solution, or to increase the concentration of hydronium, I really should say, and to make ammonia molecules, which are also in solution. Because it's an equilibrium, I can actually write an equilibrium expression for this, and because it's making a hydronium, it's a Ka expression. And that's interesting, because we're given a pKa, so it's going to be quite easy to work with. And so I fill this out. Sorry about leaving out states of matter, but that's just for speed. And I actually know quite a few of these values. Ka from pKa is going to be 10 to the power of negative 9.23. These two are going to be the same or very, very close to it. So I can put x squared up here. Or can I? And this is where it's a key thing. In here, there will be a little bit contributed by the dissociation of water, although we make the assumption that that's not going to change the pH much. So even though technically there probably will be a little bit more hydronium than ammonia molecules, we leave it as this assumption because there's only 10 to the negative 7 moles per litre of hydronium contributed by the dissociation of water. So this is a fair assumption to make. And the last thing we've got is the ammonium. So with that assumption goes the fact that this will still be 0.02 moles per litre from the question. And that's because it's a weak acid. If it's a weak base, it's also a weak acid, so it's an equilibrium system. So there'll still be a very high concentration of ammonium ions in there. So if I rearrange this, it's a bit like doing a weak acid. X, which is going to be our hydronium ion concentration, is equal to the square root of Ka times the acid concentration. In this case, the acid is the ammonium ion, so times 0.02. As we do that, so 10 to the power of negative 9.23 times 0.02 equals, then we square root that answer, and we get 3.43 times 10 to the negative 6 moles per litre. That's very low, but you'll notice that it's less than 10 to the negative 7 moles per litre. If it was higher than 10 to the negative 7 moles per litre, you know you've made a mistake, because this is making hydronium ions. It has to be an acidic salt. So that's something to take note of when you get these numbers, that you are actually getting an increase in hydronium ion concentration above 10 to the negative 7. By the way, that would probably mean that this 3 is wrong, because if that's the 10 to the negative 6, that's 10 to the negative, if that's 10 to the negative 6, that would be 10 to the negative 7 placeholder. So we're going to ignore that for now though, that's not that important. Because that's our hydronium ion concentration, we can now work out our pH, negative log base 10 of that number there. And that's 5.64. And Again, we just check, yeah, that's less than 7. So in my equation, I better have hydronium made, and I do. If this had made hydroxides, I'd work it out the same way as doing a weak base. So if you need to check how that's done, go back to a previous video on that. A good example of that could be sodium ethanoate, where the ethanoate ion makes ethanoic acid molecules plus hydroxide. So therefore you have to treat that as a weak base in that particular case.